Welcome to this video about the basics of logistic regression. To understand the basics behind logistic regression, we'll first discuss the differences between linear regression and logistic regression. Remember that linear regression requires that the dependent variable, the one we put on the y-axis, should have a continuous scale. In this example, we like to predict how the prostate-specific antigen concentration in blood changes during aging. We have collected 8 individuals at different ages and measured their PSA levels. Note that this is just a fictive dataset created for the purpose of this video. For example, this person is 82 years old and has a PSA concentration of about 3.4 micrograms per liter. By fitting the linear regression model to the data, we can estimate the parameters b0, the intercept, and b1, the slope. For this example data, the intercept was estimated to 0.4 and the slope to 0.02. The estimated intercept tells us that a person at age 0 is estimated to have a PSA level of 0.4. Whereas the estimated slope tells us that the PSA level increases by 0.02 each year. By using this equation, we can for example predict that a person who is 8 years old should have a PSA level of about 2 micrograms per liter. We can make the same prediction by drawing a vertical line where the x-axis is equal to 80, and then the horizontal line from the regression line to the y-axis. We see that by using the regression line, we can predict that a person at age 80 has a PSA level of about 2. We'll now introduce logistic regression. Suppose we have the following data. Note that this is just fictive data where the values have been selected for the purpose of this video. The variable on the y-axis is on nominal scale with only 2 categories. The variable on the y-axis represents if someone has prostate cancer or not. For example, these 7 individuals have prostate cancer, whereas these 7 individuals do not have prostate cancer. Note that no data point can exist in this region since the y value has to be either yes or no. For example, this person has prostate cancer and a PSA level of about 3.8, whereas this person from the healthy control group has a PSA level of about 2.5. Let's change the labels on the y-axis so that 1 is used instead of yes and 0 is used instead of no. If you now try to fit a straight line to this data, it will result in a very bad fit. For this type of data, it seems better to fit an S-shaped curve that can only take values between 0 and 1. The following logistic function can be used, which can generate an S-shaped curve that is constrained between 0 and 1. When we use the logistic function for this kind of data, it is called logistic regression. We'll later see that the y-axis can be transformed into logged odds, which makes it possible to fit a straight line to the data. So far, we can conclude that the main difference between linear regression and logistic regression is that, first of all, in linear regression, the variable on the y-axis has a continuous scale, whereas in logistic regression, the variable on the y-axis has a nominal scale with only 2 categories. The second difference is that in linear regression, we fit the straight line to the data, whereas in logistic regression, we can imagine that we fit an S-shaped curve to the data. In another video, we'll cover the details of how the model is actually fitted to the data by the maximum likelihood method. We will now use the following dataset to see how the y-axis can be seen as a probability between 0 and 1. Note that we have a bit more data points this time, because it will help to explain how we can estimate the probabilities. Let's cut this plot into 6 pieces. We then calculate the proportion of individuals within each range that has prostate cancer. For example, in the PSA range between 0 and 1, we have only healthy individuals, which means that we have 0% of individuals with prostate cancer. In the range between 1 and 2, 1 out of 5 or 20% have prostate cancer. And in the range between 2 and 3, 3 out of 6 or 50% have prostate cancer, and so forth. Let's create a plot where we show the fraction that has prostate cancer in these 6 ranges. We can add a point in this plot that shows that with a PSA level of 0.5, which is the midpoint in the first range, we have no prostate cancer patients. Then we add the point for the second range, where 20% of the individuals have prostate cancer. And then we add for the third range, and then for the other ranges. If you fit the logistic curve to these data points, the curve will fit very well to the proportions. We can use this curve to estimate the proportion that has prostate cancer in our sample. The curve can therefore be seen as an estimate of the proportion of individuals that have prostate cancer given a certain PSA level. For example, for a PSA concentration of 2, we expect that 20% of the individuals have prostate cancer. And for a PSA concentration of 3, we expect that about 70% of the individuals have prostate cancer. We can also think of the y-axis as the probability that a person has prostate cancer in this sample for a given PSA level. Note that the probability that you have a disease also depends on the prevalence. The predicted probability for a given PSA level is therefore only valid for this study group, where we have collected a certain number of patients with prostate cancer and a certain number of healthy controls. Watch the lecture about the positive and negative predictive value to see how the prevalence affects the probability that you have the disease, given a positive test. In this example, we see that the probability that a person with a PSA level of 3 has prostate cancer is about 70%. The logistic function that is used to draw this curve looks like this. The left-hand side represents the probability for prostate cancer for a certain PSA concentration. E is the Euler's number, which is approximately equal to 2.718. B0 and B1 are the parameters that we like to estimate, similar as we do in linear regression. By using a statistical software, we can compute the optimal values for B0 and B1 that gives us a good fit to the data. For this dataset, B0 and B1 were computed to -5 and 2. Let's plug in the values for B0 and B1 in the equation. With the help of this equation, we can now predict the probability that a person has prostate cancer given a certain PSA level. For example, if we set the PSA variable to 3, we see that the predicted probability that a person with a PSA concentration of 3 has prostate cancer is about 73%. We'll get the same prediction by using the plot if we draw a vertical line at 3 until we hit the curve, and then a horizontal line which intercepts the y-axis at about 0.73. We'll now use the following example data to explain how we can transform the estimated probabilities into logged odds. Note that we in this example have a bit fewer data points than in our previous example in order to simplify our calculations. In total, we now have 7 patients with prostate cancer and 7 healthy controls. For example, the first person in this dataset has prostate cancer and a PSA level of 3.8, whereas person number 8 is a healthy individual with a PSA level of 2.5. If you use logistic regression on the following data, B0 is now estimated to minus 5.75 and B1 to 2.75. By using this equation, we can compute the probability to have cancer for each person in the dataset given their PSA levels. For example, the estimated probability that person number 6 has prostate cancer based on its PSA level of 2.1 is about 0.5. We will get the same value if we use the fitted curve, since the curve has been generated based on the equation with the estimated parameter values. Let's compute these estimated probabilities for all individuals. If you now plot these estimated probabilities as points on the curve with x coordinates that correspond to the corresponding PSA levels, the points will be located on the curve like this. The coordinates of these points correspond to the measured PSA levels and the estimated probabilities according to the logistic regression model. In this lecture, we'll not go into the details of how the probabilities can be converted into odds or logged odds. Instead, we just accept that the odds can be calculated like this. To calculate the odds, we divide the probability for having prostate cancer by 1 minus this probability, which corresponds to the probability of being healthy. For example, if we calculate the odds for person number 2 with a corresponding probability of 0.97, we get a value of 32.3. We can think of these odds as, if we have 33.3 individuals with a PSA level of 3.4, one of these individuals will be healthy, whereas the other 32.3 individuals will have prostate cancer. Let's calculate the odds for the other rows as well, using the same equation to convert the probabilities into odds. Note that the odds have been calculated based on the rounded probabilities for the purpose of this video. Next, we compute the natural logarithm of the odds so that we get the so-called logged odds. We see that the logged odds will be negative if the odds is less than 1. And if the odds is greater than 1, the logged odds will be positive. If the odds is equal to 1, the logged odds will be equal to 0. As an example, the natural logarithm of 6.69 is about 1.9. Note that the probabilities take values between 0 and 1, whereas the odds may go from 0 to plus infinity. In contrast, the logged odds can take any values from minus infinity to plus infinity. Let's plot these logged odds so that we can see how the logged odds change over different PSA levels. Note that the logged odds seem to follow a straight line. For example, the predicted probability that person number 8 has prostate cancer is 75%, which corresponds to a logged odds of 1.1. We now fit a straight line to the data points. Note that the data points fit perfectly on the line. Remember that we use the following equation to fit the logistic curve to the data, when the y-axis was expressed as a probability. The estimated values of B0 and B1 was minus 5.75 and 2.75. We can transform that equation so that the left-hand side is expressed at logged odds instead of a probability. How we do this transformation will be discussed in another video. Note that the right-hand side now includes a linear term. This equation can actually be used to draw this line. We can now interpret the coefficients. Minus 5.75 is the intercept on the y-axis when the PSA concentration is equal to 0. The logged odds when the PSA level is equal to 0 is therefore estimated to minus 5.75. The slope of this line is 2.75. This means that if we increase the PSA level by 1 unit, the logged odds is increased by 2.75. Let's add two arbitrary points to this line. When the PSA level is equal to 3, the estimated logged odds is equal to 2.5, whereas a PSA level of 4 results in an estimated logged odds of 5.25. Then we antilog the logged odds of the first point, which results in an odds of 12.2. And do the same for the second point, which results in odds of about 190.6. We then calculate the ratio of these two odds, which gives us the so-called odds ratio. We see that the odds ratio is equal to 15.6. A faster way to calculate the odds ratio is to simply antilog the estimated value of the slope of the line. If we antilog the estimated value of the slope, we get the estimated odds ratio. Thus, the estimated value of the slope is equal to the logged odds ratio. This conclusion is important because it tells us how we should interpret the estimated parameters from logistic regression. For example, the odds for a PSA level of 4 is 15.6 times greater than the odds for a PSA level of 3. If we run logistic regression on our previous data in the statistical software, we'll get an output that might look like this. The intercept in this case is of little biological interest, but we know that minus 5.75 represents the intercept on the y-axis expressed as the logged odds. The slope of the line is estimated to 2.75, which is our logged odds ratio. Since the corresponding p-value is less than 0.05, we know that the logged odds ratio is significantly greater than 0. If we antilog this value, we'll get the odds ratio for 1 unit change in the PSA level. Remember that we can also calculate the probability for a certain PSA value if we plug in the estimated parameter values in our previous equation. If we plug in the estimated parameter values for B0 and B1, then we can, for example, calculate the probability that a person with a PSA level of 2.5 has a 75% risk of having prostate cancer in our sample. However, remember that the probability for having the disease given a certain test result is dependent on the actual prevalence, as we discussed in the lecture about the positive and negative predictive value. Also, since the PSA level is known to increase during aging, it seems reasonable to include the variable age in the model so that we can predict the probability of having prostate cancer based on both the PSA level and the age. We will discuss logistic regression models with more than one explanatory variable in future videos. This was the end of this basic lecture about logistic regression. In other videos, we'll have a look at how logistic regression can be used as a classifier to, for example, tell if someone has a disease or not, and how to compute things like sensitivity and specificity and ROC curve based on logistic regression. In another video, we'll see how we can use the estimated odds ratio to analyze if there is an association between a factor and a disease, similar to what we do with the chi-square test. We'll also see how logistic regression can be used to select the best model, and how a model is fitted to the data by using the maximum likelihood method.